Hey everyone, so this is the video for the direct shear lab. Um, as you can see, it's the direct shear lab. Um, there's going to be two parts to this lab, so it's going to be the lab, and then I want you guys to watch a pretty cool video and then answer the video questions and include that in your report. Um, as always, if you guys have any questions, just email me or call me or text me. I should be around. So, um, yeah, anyway, we'll start this lab off with a joke. So, what do you call a wolf that has everything figured out? If you guess correctly, it's a werewolf. A werewolf. Get it? As in AWARE. LOL. I like that joke a lot. Anyway, so we're doing direct shear this week. A little bit different from the consolidation lab, but some of the same principles. So the direct shear lab measured deformation just from the pressure that's applied at the top, but for this direct shear lab, we actually have a pressure that's not only applying vertically, but also horizontally. And so we're going to measure and kind of record these failure envelopes, is what we call them, and figure out exactly when our failure of our soil occurs. So this type of test is used for cohesive or cohesionless soils. Normally you'd have an undisturbed or remolded sample. It's used to find your C prime and your phi prime values. And it's used to measure the relationship between your normal shear and your shear, or your normal stress and your shear stress at failure. So we're told that our soil is a diameter of 2.5 inches and a height of 1 inch. You put it into a fairly similar apparatus as before, except there's another little part of the machine that applies a force horizontally. So during this test, there's 3 different values of P that are applied. So P is the force being applied vertically. T is constant. And so the forces, or there are 3 different values applied until it fails. So, and then you record the deflection and horizontal displacement as T increases. Sorry, I misspoke. T is held, T is increased each step, and then the P is constant. So these 3 different lines here is 3 different values of P at an increasing T. So sigma 1 is less than sigma 2, which is less than sigma 3. As P increases, shear resistance also increases. We're going to use our peak values to pull off our failure values. And then using this information, we can also figure out what our C prime and our phi prime is. So kind of the overall goal of this lab is to develop these 2 different graphs and pull off these 2 values. So I hope you guys enjoyed the Excel lab of the consolidation, because we're going to be doing more Excel. I promise it's not going to be as brutal. This should go much quicker. This should be very, very painless. So the pros of this test is it's inexpensive. It's relatively fast for cohesionless soils. It's simple. The cons, forces a horizontal shear plane, not necessarily the weakest, and it's kind of hard to control the drainage during this test. So as you guys can see, we have all these different equations over here. So horizontal load cell, vertical load cell, deformation, horizontal actuator, shear stress, vertical stress, average normal stress. And what we're basically given is the data that the computer would record from our sample. We're not actually going to run the samples ourselves. And so we're going to run these calculations for the 4,000, 2,000, 1,000 PSF tabs. And then we're going to kind of follow the instructions on the spreadsheet. And yeah, so let's kind of dive into the Excel and we'll come back to what I'm expecting for the memo. So let's see. So this is what you guys are given. This is what the computer will spit out at you. So as you can see, we have a lot of similar information as what we received for the consolidation lab. So we have calibration factor, zeros, stuff like that, horizontal load cell, vertical load cell, deformation, all that fun stuff. So our goal is to fill out these columns right here. So we're going to fill these out. These are the different steps. So we have 4,000 PSF. This goes all the way down. And then the next two tabs are just 2,000 PSF and 1,000 PSF. And so basically what you're going to do is you're going to fill these columns out for each one of these tabs. So 4,000, 2,000, 1,000. And then you're going to find your graph of your shear stress versus shear displacement that kind of looks something like this, where we have our three different distinct peaks. And then using our Moore diagram, we can figure out our failure envelope. So hopefully this will automatically graph for you. There's some instructions here on the right. I tried to make them pretty simple. If you know how to fit a line of best fit to this data, it should be pretty straightforward. So this is kind of what I'm looking for at the end. So this is all of it filled out. So as you can see, we have our different values for our horizontal load cell, our different equations. Those equations are just outlined in the notes here. So when in doubt, consult the notes. And so we have our horizontal load cell, we have our vertical load cell, our deformation, our horizontal actuator, our shear stress, and our vertical stress. And so as these plot, we're basically just going to drag these down, and we're going to find all these different values. We're going to do that for each 4,000, 2,000, 1,000. So as you can see, you got to make sure that you're referencing the right things and the right tabs, stuff like that. So I don't really feel like I should walk through Excel with you guys again. If you get really confused and you don't know how to absolute reference something, or you don't know how to include pi, or if you need just general assistance, let me know. But you should end up with a graph like this, right? And since we all have the same values, we all should get the same graph. If your graph is upside down, there's probably a negative missing somewhere. Your graph should be the exact same as mine. So it should have these three different distinct peaks. And what we're going to do is we're going to pull off these values of where it fails at that part of the experiment. So as you can see, this one, if I hold my cursor over it, it's 3,500. This one's about 2,100. And this one's about 1,200. So if we go over to our Moore diagram tab, so we have our average normal stress at the that the experiment is trying to apply. So 4,000, 2,000, 1,000. As before, it's not going to apply that directly, so we're going to take an average. That's what this average is here. So it just takes an average of all these values down here, and try to omit any outliers that you see on either end. So we have these three different values. We pull off our average peak shear stress values just from this graph right here. And what we're going to do is we're going to graph these. And so what we're going to do is my bad. So for back here, so what we're going to do is we're going to fit a couple different lines of best fit to this data. So I hope you guys know how to do this. I'll show you one. The instructions on this sheet are pretty straightforward. So graph normal stress versus shear stress. So graphing these two. And then, so that's all these blue dots right here. Fit a linear line of best fit directly through the data and determine the intercept, which is the cohesion, and the slope in degrees which is the friction angle. Fit another line or another linear line of best fit through the data, but have it intersect the origin with the cohesion set to 0. Determine the corresponding slope in degrees, which is your friction angle. And then fit a third trend line that is polynomial line through the data and set this line of best fit to have an intercept of 0. And then we're just going to display those equations up on the chart. And so I'll do one example for you guys right here. So if you graph your data and you right click on your data and you hit add trend line, so now we have this beautiful trend line that just fits right through our data. It will pull up this nice little chart over here. So we can use this forecast option and we can say forecast 1,000 periods backward, and we can also say display equation on chart. And now we have these two different values. So 503, that's going to be our C. That's going to be our intercept. So that's going to be our cohesion. So that's in PSF. This value right here, 0.7525, is our phi. So if we just take the arctangent, arc cosine, not exactly sure how to take the arc, oh, a tan, okay. So equals a tan of 0.727525, and that's going to be 65 degrees. Why did that not work? Oh, that's because that's in radians. So you're going to have to convert that to degrees. And that should come out to 37 degrees. So if you do it on your calculator, it might be a little bit easier. And then using this data, if you right click again on the data, you can hit, you have to be sure you click right on the dot, not on the trend line. There we go. Then you can add another trend line and you can say set intercept to 0, forecast backwards about 1,000, and then just be sure to change the color of it, make it something different than the black line, and then you can also say display equation on chart, and you're going to find that this is your equation right now. So now arctangent of 0.92 should be around 43. Your C is just 0. So pretty straightforward. I don't think I should need to go through that again, but yeah. And then so that's basically all you do for the Excel part of it. So now we have these values. Now if we go back to what we're expected of for the rubric, so I want a to, from, date, lab, location, etc. I want your table with your average normal stress and your max shear stress, so that's on your more diagram tab, so this table right here. I want your failure envelope information, so your phi prime and your C prime. Be sure to include your units on those. And then I'm going to have you guys actually do this in the last lab, so ignore this for now. Let's write one paragraph about your favorite lab. And so since we haven't done all the labs, I'm going to have you guys do that the last lab. So for your attachments, I want you guys to print out your shear stress for shear displacement graph, print out of your more diagram graph, and include all your sample calcs. So conversion equations, C prime or phi prime, C prime, and be sure to include your video worksheet as well of the Risa landslide video. And like I said before, all the equations are right here. If you get confused, just shoot me an email. All the stuff is kind of outlined for you on this Excel spreadsheet, so it should be pretty easy. And yeah, this is kind of what you're after. This is mainly what you're after. And this is kind of just describing the overall procedure, so I'd go through this and read through it since I can't be there to explain it to you guys in person. And yeah, so this will be due April 23rd by 5 p.m. in the assignment folder. So I set up another assignment folder for you guys. If you're having trouble submitting it, let me know. This is the link to the video. Be sure to start the video from the beginning. And yeah, if you guys have any questions, it should be, I'm also going to put it on YouTube in case for some reason it's not working on D2L. Just kind of have a backup. So yeah, that's all for now. Hope you guys have a good day. Thanks. Bye.